When we're working with roots, we're really working with exponents too. In a way, we're undoing exponents. So for example, with the square root, we're thinking of the square of a number. So our definition, the square root of x squared is equal to x. So what we're doing is we're trying to find this value that would be under a square when we're taking the square root. So for example, 2 squared is equal to 4, coming from 2 times 2. So the idea is when I'm looking at the square root of 4, I'm thinking what squared would give me 4. So what we could do is have a step where we say 4 is the same thing as 2 squared. And with that, this radical that is a square root and that exponent of 2 kind of cancel each other out. So then what we're left with is an answer that is this base of the exponent, which is 2. So that outcome is that base of the exponent, which is 2. Similarly, we can take different level roots. So like we'd have a cube root. And with that, we're thinking what cubed gives us the value underneath the radical. So with the cube root, say we're taking 2 cubed, well, that's the equivalent of 8. So if I'm looking at the cube root of 8, I'm thinking what cubed would give me a value of 8? All we could do is, like we did up above, is rewrite it as the cube root of 2 cubed. And again, this cancellation occurs between the cube root and the cube of a value so that we're just left with the base of that cubed value. So if we're trying to answer what cubed gives us 8, well, that answer would be 2. So on and so forth. We can take the 4th root, and with that, we're thinking about what raised to the 4th power gives us our value underneath the radical, all the way up until we could take the nth root, and we're trying to think of what base do we need under an exponent of n to give us the value under that radical. So to the n power, what I would be doing is if I'm looking at the nth root of 2, nope. Yeah, I can write it this way. And I can express it as 2 to some power of n, we get this cancellation to just be left with the base underneath. So as we're thinking about roots, we're also thinking about bases of exponents. So let's talk about some terminology here with all these values kind of floating around. So this is the nth root of a. That's how I would read that out loud. So the nth root of a. Now, some terminology that we use, the symbol itself, this symbol right here, that is called the radical. That's the radical symbol. The value for n is called the index. It's telling us what type of root that we're taking. So that's our index. And then the value underneath the radical, so this value of a, is called the radicand. So we have these 3 pieces all coming together to have us evaluate a root. Okay, so when we're taking roots, we're thinking about the principal root. So as I was talking about up above, like if I'm looking at this root of 25, what I'm thinking to myself is what squared gives me 25? Or let's say results in 25. Now, if you reflect on when we were solving quadratic equations and say I was looking for, okay, I'm thinking of x squared equals 25, and we took the square root of both sides, and what we ended up with was x equals plus or minus 5. We had the positive and the negative because 5 squared is 25 and negative 5 squared is also 25. And our whole goal there in solving was finding all possible solutions. So with this, we were solving an equation for possible values for x. What's changing a bit here is here we're simplifying. We're simplifying a radical expression. And with that, we're not looking for all possible solutions. We're kind of looking for, and it's not really a solution, it's just another way of expressing this. So our rule goes that if we're looking for simplifying radicals, we only use the principal root, which is just the positive value. So if I asked you to simplify the square root of 25, we would only use the positive value of 5. If I wanted you to simplify the square root of 9, then you would just give the result of a positive 3. So with simplifying, we use the principal root, but don't mix that up with when we're solving equations where we want all possible solutions. When we're solving equations, we want to think about our square root property and where we have the plus or minus. So we need to be careful of these two scenarios and keeping them separate, but when we simplify, we just use this principal root. Another thing we need to be careful of is the idea of negative radicands. So having a negative value under the radical symbol. Now, if we're taking an odd root, so if we have an odd index, that's totally fine. We can do that. We cannot take the even root of a negative radicand. So let's talk through that with these examples here. So the square root of -4, again, what I'm kind of thinking to myself is, what squared would give me a result of -4? Or I could think of what times what would give me a -4. Well, I know numerically I would need 2's multiplying, but they either have to be both positive or both negative, and both of those cases is going to result in a +4. So what happens is, because it's an even index and we're trying to make these pairings, it's always going to result in a positive number. Either having them all positive or all negative, it'll always give a positive result. So even if these were both -2, that would give us a +4. If they're both +2, they also give a +4. So there's no way for us to make that work. So with that, this is no solution. Let's go with does not exist, because we're not really looking for solutions here. We're just trying to simplify. And we can't simplify. So similar thing happens here. I'm thinking, what multiplying with itself gives me a -16? And because I'm taking the 4th root, I would have 4 pieces multiplying. Now numerically, it would be 2's. 2 times 2 times 2 times 2, give me 16. But they all have to be negative, or they all have to be positive. And even if they were all negative, that would be a +4 times +4, so we'd get +16. This is another case, because of that even index with a negative radicand, it can't happen. We can't make that work. So this is another case of does not exist. So what if we take an odd root? So with this, I want 3 things multiplying to itself to give me a -8. Well, numerically, it's going to be 2's multiplying, and they all have to be positive or all have to be negative. Now the all positive doesn't work because that'll give a +8, but let's see what happens if I make them all negative. So that would be a +4 times a -2. That gets us to our -8. So when we have an odd index, this works out that we would want to have -2 cubed would give us a -8. So our solution, or rather how we would simplify that, is down to a -2. So that works out. If we have an odd index, we can evaluate the negative radicand. Here, same thing, the fact that I could rewrite this as the 5th root of -2 to the 5th power. So with that, we would just have a result of -2, and it works out because of the odd index. Okay, so in simplifying radicals, we want to grab whatever we can out from underneath the radical. We want to simplify that radicand as much as possible and bring anything outside of the radical that we can. And in order to do that, we might need these properties. One is the product property. So if we're taking the nth root of values that are multiplying together, we can separate that as the nth root of A times the nth root of B. So what we can do is, if we have a value underneath a radical, we can separate it into its factors. And another piece we can do is use a quotient property, where if we have values dividing underneath a radical, we can separate it as the nth root of the numerator divided by nth root of the denominator. And something we'll talk about is in simplifying radical expressions is that we do not want to have radicals left over in the denominator. So with that, we'll have a step called rationalizing the denominator, which we'll talk about in the next videos. But it'll be something to think about is for a simplified expression, we should not have radicals showing up in the denominator, so we would take steps to fix that. Okay, let's go through some examples here of using those product and quotient properties, as well as our properties of up above, of simplifying these. So, square root of 32, first thing I would think about is, okay, what squared gives me 32? But there is not a nice answer to that. So this isn't going to be a perfect square root. So something we want to do is break up 32 into factors. And there's going to be some different ways to do that. So with this, I'll show you two different ways to go about it. One way is kind of the long way, and it uses the prime factorization. I do like it because it does exhaust all of the possibilities. And another way is looking for factors that are perfect squares, which can be a little shorter, but sometimes it takes a long time. So how about let's go through prime factorization first over on this side. Oh, that's a big word. It's going to go into that next spot. So what I'm doing is I'm thinking of 32, and I want to just kind of start breaking it apart. So like I know that comes from, and you can do any pairing of two values that multiply to 32. How about 4 and 8? Well, I know 4 is made up of a 2 and 2. I know 8 is made up of a 2 and 4. And 4 is made up of a 2 and 2. So I'm just dividing up those pieces until I end up with only prime values. So with that, I could break down 32 to be expressed as a 2 times 2 times 2 times 2 times 2. So let's see what that looks like underneath the square root symbol. So we have 2 times 2 times 2 times 2 times 2. Now, because I'm doing a square root, I'm looking for pairings because I want, in this case, it's going to come through as 2 squared, but I'm looking for values squared. So here's a 2 squared, here's a 2 squared, and then we have a 2 left over. So what this is going to do is, there's a few ways to write this, but basically this is going to, if I have my radical symbol in the next step, this brings a 2 outside, so they can escape because we have a pairing and we're taking a square root. This also brings a 2 outside, so those are going to multiply together. And then this 2 that's left over that does not have a pairing, that's going to stay underneath the radical. So how I would rewrite this is 4 on the outside, square root of 2. And that would be my simplified form of that. So that's the prime factorization. So you'd have all your values listed out. And then with the square root, you'd look for pairings. If you have a cube root, you'd look for threesomes. With a fourth, you'd look for groups of 4. So it adjusts based on the index. Another way you can do it is thinking about the factors of 32. So like 1 and 32, 2 and 16, 4 and 8, and that'll do it. And what I would be doing is I would be looking for perfect squares that are in there. So like I see that 4, I can take the square root of 4 very nicely. I can also take the square root of 16 very nicely. And what I want to do is I want to use the larger value. So I'm going to do is rewrite 32 as the square root of 16 times 2. And what we can do in the next step is using that product property up above is I could split that up. So this would be the square root of 16 times the square root of 2. Taking the principal root of the square root of 16 would leave us with a 4, and then multiplying with that root 2. So they get you to the same spot. It just depends on which method you like better. That listing factors can go fast, but sometimes if I can't quite see what the nice perfect square is, prime factorization always works. So with the cube root of 40, I'm going to go prime factorization route with this one. So if I make the prime factorization, how about 4 and 10? Which is a 2 and 2 with a 2 and 5, and there's all my prime factors. So this would be the same thing as writing the cube root of 2 times 2 times 2 times 5. Now because this is a cube root, I'm looking for groupings of 2. So with that, the 2 is going to come outside, 5 is going to be stuck underneath. So because I could make a grouping of 2's, 2 out front, cube root of 5 with the 5 still stuck underneath. One way to do it. The other way would be to see that 40 is made up of 5 times 8, which 8 makes a nice cube from 2 cubed. So we could have write this as the cube root of 8 times the cube root of 5, and the cube root of 8 would be 2 times the cube root of 5 to get to that same answer. Okay, you only need to do one method. I'm just showing you both so that you can get comfortable with trying these out. And again, it's just whichever works best for your brain. Okay, square root of 75x cubed. So that's where I like to look at the prime factorization, because with x cubed, we would be thinking of x times x times x. So we could see we have a pairing in there. 75, let's go ahead, and I'm just going to think about factors, which sometimes a calculator will help out with these. How about 75 divided by 5 would be a 5 and 15. Oh, we'd have a 25 times 3. I think that's going to be a good one because 25 is a perfect square. So what I could do is rewrite this as 25 times 3 times, and then with x cubed, because I want to look at the pairings, I could rewrite this as x squared times x. So I can see the values that I'm going to take the square root of. I'm going to take the square root of 25. I'm also going to take the square root of x squared. So square root of 25 is 5, so that'll come outside. Square root of x squared would leave us with an x. And then trapped underneath the square root, we still have a 3, we still have a 1x. So that would work. Could write out the prime factorization, and you should get the same result. Root 4 over 25, what we could do is use our quotient property. Since 4 divided by 25 doesn't simplify at all, then what we could do is split this up as the square root of 4 over the square root of 25. Well, the square root of 4 is 2, over square root of 25 is 5. So we would have a positive 2/5 for our answer there. And then our last one here, we could do the same thing of splitting it up. What I do start with is first I see if there's anything I can simplify underneath the radical. So in the radicand, it's all simplified, so now I'm going to split it up to square root of 8x squared over square root of 9. So square root of 8x squared, what I could do is think of 8 as a 4 times 2 times x squared. Square root of 9 is a positive 3. And then I could see up above, so square root of 4 would bring a 2 outside, square root of x squared would bring x outside, and then I would still have a 2 trapped underneath, all over 3. Then in terms of further steps of simplifying, I would see if anything outside the radicals can cancel, which there isn't. always be careful that something that's underneath a radical cannot cancel with something outside of a radical. So we don't really even have that here, but that's why I keep saying trapped under the radical, is I think of it as something that's trapped and it can only cancel out with fellow things that are trapped as well. So we either have these things outside of the radical or inside the radical, and they can only cancel with each other.